This video will talk about solving loaded voltage divider circuits. These circuits are not used extensively anymore because we have voltage regulators, but the principle applies when you're trying to use a voltage divider to output different voltages from a single voltage source, and is a great teaching method for using Ohm's law, Kirchhoff's laws, and an understanding of series parallel circuits to help solve these circuits. So we're using it as a teaching tool, not as an actual circuit that will be used. So here's an example of a voltage divider circuit, a loaded voltage divider. We actually have four loads: voltage load A, B, C, and D, and we're going to reference our voltage to the center. We're going to say that the bleeder current needs to be 10% of the total load current of the largest pole. A general rule of thumb that's given to help prevent the voltages from fluctuating wildly when the load voltages change. As demand is placed, as a load changes, that load voltage could change, but putting it in parallel with the resistor and controlling the current going through that resistor helps stabilize that voltage to the load. So the first step in solving these circuits is to figure out which load is the largest pole. To do that, we're going to take loads that are in parallel and total them together. So if we look at load A and load B, we have load A at 27.941 milliamps and load B at 46.667 milliamps. So together those add up to 74.608 milliamps. But the other pole on the bottom, in reference to ground, load C is 120 milliamps, load D 87.234 milliamps. It should be obvious that that's larger. In fact, they add up to 207.234 milliamps. So that's going to be our largest pole. So we want to take as our bleeder current 10% of that total load current. If we divide by 10, that gives us 20.7234 milliamps. That bleeder current, look at the current path that's through the circuit. We can push current using that voltage source. I'm going to use conventional flow rather than electron flow, so we'll go from positive to negative. Current being pushed from the source gets to this first node, and then we'll split, some of it going through resistor 1, the rest continuing on through resistor load A. Once it flows through resistor 2, there's a couple of possibilities here. Could, depending on voltage polarity, that could move, say, this direction and eventually go through load C. Current's going to go through load D. Current could also flow through resistor 3, and as we look at these currents, current coming from resistor load C joins up with current from load 3 to move through resistor 4. Current from these other loads, A and D, joins together with the current from resistor 4 to flow through resistor 5 and then back to the source. So if you look at the circuit here, the only current that doesn't have the possibility of flowing through a load, flowing through resistor 3. So resistor 3 is going to be our bleeder resistor. So if I take 10% of the load resistance, that's 207.234 milliamps, so 10% of that would be 20.7234 milliamps, and that's going to be flowing through resistor 3. So there's my current 3. Now we start using a combination of Kirchhoff's current and voltage laws and Ohm's law to solve this circuit. So when you realize that resistor 4 current had to come from resistor 3 and resistor load C combined, then we can use Kirchhoff's current law to add those two currents together to get current 4. So that would be 120 milliamps plus 20.7234 milliamps, or 140.7234 milliamps. Now also, when we look at resistor 3, we realize that it's in parallel with the load C resistor. Load C resistor is at 12 volts. So a parallel relationship between resistors means that voltage drop on resistor 3 is also going to be 12 volts. And now we can use Ohm's law to solve for the resistance of resistor 3. Also, we notice the voltage load D is 41 volts. 12 of that is found in the parallel combination of resistor 3 or resistor load C. So if we take 41 minus the 12 volts, that would give us what has to be the voltage drop of resistor 4, or 29 volts. Next, if we use Kirchhoff's current law from resistor 4 current and current load D flowing together, then we know the current passing through resistor 5, which is also the total current of the circuit, which is 227.9574 milliamps. Since we know that's the total current, coming into the node where resistor 1 branches off and resistor load A, we know that of that 227.9574 milliamps, 27.941 milliamps flows through resistor load A, leaving 200.0164 milliamps flowing through resistor 1. Then we also can use Kirchhoff's current law to know how much current flows through resistor 2, because of that current that was flowing through resistor 1, 46.667 milliamps flows through load B, leaving 153.3494 milliamps flowing through resistor 2. And again, we can use Kirchhoff's voltage laws and the relationship between parallel resistors to find the voltages. Resistor 2, which is in parallel with load B, which has a voltage drop of 7 volts, must also then have a voltage drop of 7 volts. Because that 7 volts is in series with R1, those two voltages together have to add up to the voltage drop across load A, which is 19 volts. So that means 12 volts has to be dropped on R1. And now looking at our circuit, the only voltage drop left is that across resistor 5. And if we realize that we have a loop from the source starting at 70 volts, we drop some through load A, some through load D, and the only other voltage drop left would be that across resistor 5. So if we take 70 volts, our total voltage, subtract load A and load D, what's left must be the voltage drop on resistor 5, which gives us 10 volts. And now we can use Ohm's law to solve each of the resistor values in the circuit. Because each of those have a voltage and a current, we can use the Ohm's law formula of resistance equals voltage divided by current to find resistance. So for resistor 1, we get 59.995, or roughly 60 ohms. Resistor 2 is 45.6 ohms. Resistor 3 would be 579 ohms. Resistor 4, 206 ohms. Resistor 5, 43.9 or 44 ohms. And that gives us the values of every component in this circuit. So that's how you solve a bipolar loaded voltage divider. Just means there's two poles because we're referencing our reference ground is in between the two poles. You can use the same technique to solve any loaded voltage divider, and it's a great technique for teaching the combination of Ohm's law, Kirchhoff's current and voltage laws, and the relationship between series and parallel resistors. So hopefully this helped you out solving those kinds of problems.